On a clear Tuesday morning, a city's central business district went dark. Power grids, designed with layers of protection, failed in a cascading sequence. The outage was unexpected, but it was not supposed to be catastrophic. Across the city, thousands of backup systems were in place, a silent network of readiness paid for and maintained for precisely this moment. These systems were an unseen guarantee. They promised continuity for critical infrastructure, ensuring that essential services would carry on uninterrupted, regardless of the primary grid's status. Yet as the outage extended from minutes to hours, a different reality emerged. At a major hospital, the primary generator failed to start. A crucial software bug prevented a financial firm's data from switching to its replication site. At the port, a manual failover process could not be executed. The personnel with the required access were unavailable. The very systems designed to prevent disaster were themselves failing, one by one. The unseen guarantee was broken, revealing a deep and unsettling contradiction between the promise of resilience and its practice. At its core, a backup system is a secondary standby resource designed to assume the function of a primary system in the event of a failure. These systems are a diverse architecture of redundancy. Their purpose is operational continuity. Essential services continue without noticeable interruption. Physical infrastructure, on-site generators for hospitals and factories, detect power loss, and automatically start restoring power within seconds. Digital redundancy, UPS systems, redundant servers, cloud replication, manual failover processes, procedural backups. Operators follow documented steps to restore service. Design goal: minimize downtime and data loss. Measured by two key metrics: recovery time objective, RTO, and recovery point objective, RPO. The backup system is more than just hardware and software. It is also a complex network of human participants: on-the-ground engineers, vendors and suppliers, regulators, and end users and decision-makers. This intricate web of participants collectively determines the system's fate. When a backup system fails, the first explanation often points to human error. An operator might forget to refuel a diesel generator. A technician could misconfigure a network setting. A single misunderstood step can have significant consequences when an incident occurs. Such errors are frequently rooted in inadequate training or a lack of practice. A study by the Uptime Institute consistently finds that human error is a leading cause of outages. Another facet of human error is the failure to follow established protocols. Ultimately, attributing failure solely to human error can be an incomplete diagnosis. It does not explain why the training was insufficient, why the procedure was so complex, or why the operator was under so much pressure. Beyond human factors, the physical failure of equipment is another commonly cited cause. Hard drives can experience mechanical failures. Network switches can suffer from faulty circuits. A diesel generator is a complex piece of machinery, any of which can fail. A critical aspect of equipment failure is the concept of a silent failure. The failure goes undetected because the system is not active. Backup systems can be overwhelmed by external shocks of an unexpected nature or scale. Severe weather is a primary example. A facility's on-site generator may not be elevated high enough to survive a major flood. Cyber attacks are another major external threat. The scale of an outage can itself be the external shock. A deeper look reveals a failure of imagination in risk assessment. The external shock exposes both the physical limits of the backup system and the cognitive limits of the planning that went into it. A final, pervasive surface cause for backup failure is chronic underinvestment. These decisions are often made rationally, based on a cost-benefit analysis that weighs the high, certain cost of readiness against the low, uncertain probability of a major disaster. The initial decisions made when purchasing a backup system are often the first hidden driver of its eventual failure. This procurement paradox means that a system may be selected because it is cheaper to buy, even if it is more expensive to maintain or less reliable in the long run. The initial cost-saving measure evolves into a significant long-term liability. Once a backup system is in place, its performance is often governed by a service level agreement, or SLA. While these contracts are intended to guarantee reliability, they can create misaligned incentives. SLAs typically focus on simple, easily measurable metrics like uptime, not for ensuring the backup process is robust. The SLA, meant to ensure continuity, paradoxically encourages clinging to a failing primary system. The fine print may contain exclusions for precisely the situations where the backup is most needed. The contract provides an illusion of security. A third hidden driver is the gradual accumulation of technical debt and complexity within IT systems. This creates a growing divergence between the primary system and its supposed mirror image. The failover process is no longer a simple switch, but a complex and unpredictable migration project. Organizational structure itself can be a powerful hidden driver of backup failures, creating information silos. When responsibility is divided, critical tasks can fall through the cracks between teams. In reality, neither team is backing it up. That lack of holistic ownership delays recovery with confusion and finger-pointing. The final hidden driver is a market-level force: vendor lock-in. This creates dependency, a single point of failure at the vendor level. You might think you're diversifying risk with two products, only to find both owned by the same parent, creating correlated risks. The failure of a single critical backup system effects ripple outward, triggering a cascade of economic disruptions. This initial halt quickly propagates. A manufacturing plant waiting for a critical component may have to pause its production line, leading to product shortages on retail shelves. Financial markets are another domain highly sensitive to these cascading failures. An outage at a major stock exchange can halt trading. Beyond the immediate economic costs, the repeated and visible failure of backup systems erodes public and institutional trust. If citizens lose faith in the reliability of the power grid, they may buy personal generators. If people lose trust in digital banking, they may revert to less efficient transaction methods. The failure of backup systems is rarely the result of a single, isolated event. The true source lies deeper: an interconnected system of incentives, delays, and complexity. The procurement paradox favors low upfront costs. Equipment becomes harder to maintain and less reliable. The organization is locked in. The SLA incentivizes the wrong behaviors. This discourages rigorous, disruptive testing. Actual recovery capability silently degrades from lack of real-world validation. The result is not resilient redundancy, but a brittle system. Strong on the surface, fragile underneath. It's optimized for normal operations, not survival in crisis. The failure was not a matter of if, but when. The complete connection is now clear. They form a powerful, reinforcing feedback loop. The system undervalues resilience and underproduces it. This brings us to the central, unresolved tension. There is a fundamental trade-off between efficiency and resilience. Who should bear this cost? Should individual organizations be forced by stricter regulations? Those costs will be passed on to consumers. Or should governments subsidize resilience? That would spread the cost across taxpayers. Deciding how to distribute the burden among corporations, consumers, and taxpayers remains one of the most significant challenges in our interconnected world. You've been watching System Atlas, exploring how the world's systems really work. Share your comments below. See you in our next episode.